Okay, hope everybody had a nice weekend. Everybody's staying healthy. What we want to do today is, there was one item in the last session that I didn't quite wrap up with you on rational functions, and that has to do with oblique asymptotes. Now, oblique asymptotes are linear, and I want to spend a couple minutes on that before we get to these other topics. Now, let me just make a quick comment there before I mention these other topics. If the numerator of a rational function is 1 degree greater than the denominator, like let's say you had a 5th degree numerator and a 4th degree denominator, if you divided that denominator into the numerator, you'd get a quotient that was linear. Quotient that was linear, because 4th degree divided into 5th degree would give you a linear quotient. So that type of behavior is what are called, it creates an end behavior that gives you a linear function that the rational function approaches. So I'll show you that with an example here in just a minute. The other topics we want to cover in today's session are what are called reciprocal functions, and then also composite functions. And you'll actually find this kind of easy, but it's a very important topic that's going to lead us into something new tomorrow for the next session, which are called inverse functions, and that leads us on into the other realm of exponential and logarithm functions in this course. So let's come back here now to these oblique asymptotes where the degree of the numerator is 1 greater than the denominator. If we take a problem out of the book, there's a question number 25. It's found on page 210, and it's this rational function. Whoa. Happens to be x squared minus 3x minus 4 divided by x plus 2. That's the general form. Now I want to be kind of quick on this so I have enough time for those other topics today. So feel free though to ask questions if there's something you don't follow. This is what form do we call this form? This is called the general form. What other form could we put this in? Factored form, couldn't we? Sounds like a bunch of you did some studying this weekend. That was good. Factored form. And that would be an x minus 4. These don't always factor, but this particular one happens to. And an x plus 1. Always double check when you do factoring by mentally looking at it. Your middle term, negative 4x, outer term, plus x, gives you your middle term, negative 3x. And then your negative 4 on the tail end, and your x squared up front. Okay, there's the factored form. What other form could we put this in? Quotient form. Because notice this is an improper fraction. The degree of the numerator is greater than the denominator. So we could do a long division process to get what I call a quotient form. So if we take x plus 2 and we divide this into the numerator, x squared minus 3x minus 4, x goes into x squared x times. Check my algebra as I go in case I make a mistake. Multiplying, we get x squared plus 2x. Remember now, we do not change the signs of these on our paper. What we do is we mentally subtract these items where my finger is from the items above. So this mentally becomes a negative. Added to that disappears the quadratics. This becomes a negative 2x, and negative 3x is negative 5x. Bring down the next term, negative 4. Now x goes into minus 5x minus 5 times. And multiplying now minus 5 times this, we get a minus 5x matches, minus 10. And then we mentally again change the signs here, lose the 5x's. This becomes positive 10, and negative 4 is positive 6. So the quotient form of the original rational function is going to be the quotient x minus 5 plus the remainder 6 divided by the divisor, which was x plus 2. So this is called the quotient form. Now here's why that quotient form is very useful. And this technique will work for even higher or differences in degrees of the numerator and denominator. What I mean by that, if this was, say, a 5th degree numerator, 5th degree here, and this was a 3rd degree, the quotient would be what? If this was 5th and that's 3rd, it would be quadratic, wouldn't it? It would give a quadratic quotient, 5th degree over 3rd degree, if you do long division. And you'll get a quotient form that would be quadratic here with some remainder. So you can get different types of forms. That stuff, that quotient, is still going to be define the end character, the end behavior of the function, no matter what it is. It doesn't have to be linear, could be quadratic, but the trend, if you move out for large x, way off to the right or way off to the left graphically, it'll approach whatever this quotient happens to be. Okay, now keep in mind, here's what we're doing. If x becomes large, let's say I'm going way off to the right, then look at what we're getting here for our rational function. The rational function is approaching, let's say you're at 1,000 for x. You'd be at 1,000 minus 5, so you'd be right on this value, wouldn't you? 995 plus 6 over 1,002. If you were at 1,000, you would be at 1,000 minus 5 plus 6 over 1,002, right? And what you want to observe here, I usually don't write that sort of thing down. What you usually observe is that the rational function is going to approach whatever this quotient is, so you're going to be on that quotient's value, which means you would be on the graph of this line. Slope of 1, y-intercept at -5, looks like this, doesn't it? And if you're way out to the right, you're going to be up on that line, and then this number is very close to 0, isn't it? For large x, this remainder, very close to 0, but slightly positive. So what that tells us about the rational function's graph is if I drew that rational function's quotient, y equals x minus 5, then it would look something like this. And this says that way out here to the right, we're going to be up on the line, x minus 5, plus a little bit. And the further out to the right we go, we're going to get closer to it. So we'd be coming in close to it from above, over there. Look what happens if we're way off to the left. If x is approaching negative infinity, look what happens to the rational function. It's approaching still the value on the line, x minus 5, plus, what about this if this is a huge negative number now? You with me, folks in the back? All right? If this is a huge negative number, isn't this real close to 0 still? But this is a big negative number here. Big negative here. So this is very close to 0, but slightly negative. So what that tells us is we're going to be on the line, as x goes way off to the left here, we're going to be down here on the line at x minus 5. We're going to be on the line, and we're going to be, this is a slightly negative number, so we're going to be a little bit below that. And the further to the left we come, the closer we get to the line. So we're going to be in there like that. Okay. That's an oblique or a slant asymptote, sometimes called a slant asymptote or a linear asymptote. And as I mentioned earlier, they don't ever say this in a book, but if you had a 5th degree divided by a 3rd degree, a 5th degree divided by a 3rd degree, you'd end up with a quadratic kind of an asymptote out there to the right and off to the left. Yeah.
So to find the oblique asymptote, you do long division with the quotient form.
Yes. Very good, Taylor. Okay? So you're going to do long division to find the quotient form, and then that tells you right there what your asymptote is. That's the kind of question that sometimes shows up in a book, is what is the asymptotes? Or what are the asymptotes, right? Sometimes you have verticals. Sometimes you have horizontals. Sometimes you have an oblique one. Okay? It's what it is, it's the end behavior. Mm-hmm.
So that would be the end behavior, and then it's 6 over x plus 2, you just ignore that in regards to the asymptote?
We don't ignore the 6 over the x plus 2, but why is that? Why was that useful? What did that help us do without just pulling out our fancy calculator and drawing the picture? What did that help us? It helps us tell what? Yeah, if it's coming in to the top of that, above that asymptote like it is out here, instead of coming up from below. See, it tells us we're coming in from above because that's a little bit positive there. Off on the left, in this case, it happened to be a little bit below the asymptote. Okay, with a little bit of practice, that'll make sense to you. It's a fairly minor point. It's not critical for your life in algebra, but it's a subtlety that's part of rational functions.
So is that why you leave it off when you say the y equals quotient?
This remainder?
Right.
Yes. Yeah. Well, in the limit, you're going to be on that line. In the limit, as x goes towards infinity, that term will disappear.